So till yesterday we have looked into, yeah, I'll share it, Anush. It's taking some time. I'll do that. So let us go about this now actually. So we have yesterday discussed about gauge RNR and attribute agreement analysis. And today we'll be discussing about logical validation. When the metric that we have chosen is such that conducting an MSA is not possible or not practical, then we go ahead doing logical validation. But first preference should be given to MSA, measurement system agreement. Either do gauge RNR or attribute agreement analysis. If you feel that both of these are not possible at all, then you do a logical validation to check whether the data is reliable and accurate or not. This logical validation can be done by checking at the boundary conditions. That means what is a start point, what is a stop point. Yeah, are people correcting that properly or not? Here is an example. Copier repair time. That means your photocopy or Xerox. People recognize photocopy by Xerox, at least in India, because Xerox is a big company which is into photocopy. So this is how you do logical validation. What is the start point? Is it the time started when the copier is really broken? I mean, repair time. You want to capture the repair time. When did the problem occur? By what time did you fix? I want to know that time, for example, right? So is the time started when the copier is really broken? What if the time is recorded at the end of the day? Copier failed in the morning, but you captured the time in the evening. Is the time recorded in system when copier person is there to fix? So when did you actually start the timer saying that yes, I have a problem in my copier, let me start the time now? And just give me a minute, let me fix this right away. I see that there is a small problem here. All right, this is not start point, this is stop point actually, so my bad. This is the stop point. So is the time stopped when the copier is really fixed, or when did you stop the timer? What if the person who has come to repair or fix your copier has fixed the problem at say 11 a.m. 11 a.m. he has fixed the problem, but you have recorded the time at the end of the day. It's going to give you wrong time. What if the time is recorded even if the copier is not fully fixed? Right? Just because repair person has shown up, you're telling that yeah, he has come, he has went away. But are we really looking into what was the real problem and was it fixed or not? Yeah, there are a few corrections. I need to make a note of this. All right. So is this clear, Anuj? Logical validation. Logical validation you do when MSA, measurement system agreement or measurement system analysis, if that is not possible, only then you do logical validation. For continuous data, you do gauge RNR. For attribute data, you do attribute agreement analysis. If these two are not possible, only then you go ahead with logical validation. In logical validation, you calculate the start point and the stop point. When do you want to start? When do you want to stop particular problem? Yeah. And here are a few more examples. A project is selected to reduce the inventory of finished goods to less than 1 day. Yeah, I want to reduce my inventory. So what is the metric? Number of finished goods stored in a month for more than 1 day divided by number of goods produced. This data is discrete data. Number of goods. You cannot say I have one television set, or you can say I have one television set, two television sets, three television sets, so on and so forth. But you can never say I have 5.25 television sets, 6.75 television sets, so on and so forth. And the daily production and dispatch happens through system, and the data is entered in SAP. Now if you want to validate the data, daily dispatches and daily production in SAP can be verified, because SAP already has that timestamp that can be verified with the physical movement and the actual production respectively. So you can just do a logical validation, check whether the daily dispatch time, is it recorded correctly or not? Is the daily production time entered correctly in SAP or not? Alright. So we are still in the measure phase. We have completed the step 4 and 5. Now we have to do step 6. We have to measure the current performance and where do we stand as of today. Yeah. Here are various ways of baseline. Sorry. So the first thing is measures of central tendency and dispersion. How do you measure the central tendency? There are multiple ways. Either you can use mean, or you can use median, or you can use mode. Well, there are many ways of dealing with central tendency. How do you deal with dispersion? You either use a variance or standard deviation, or you can also use interquartile range, right? IQR from box plot. All right. Then you have run charts. Run charts is used to check for randomness. Always your data should be random. There should not be any trend. For example, there should not be any seasonality. Seasonality meaning power consumption increases in summer and decreases in winter. Again it increases in summer, again it decreases in winter. So this is called as seasonality. So these kind of trends should not be there. Or if you plot the data using a run chart, if the data is like this, what does this mean? Your data is increasing. So these kind of trends also should not be there in the data. So you check for randomness. Data should be random. And then we check for the shape of the data. Is the data that we are dealing with normal or non-normal? We check for that also. And then we come up with the sigma level. When we want to calculate the sigma level, we can either use DPU method, defects per unit, or defects per million opportunities method, or we can use yield method. These are all the methods for normally distributed data. What if the data is not normally distributed? If it's not normally distributed, what method are you going to use? So we will look into each and every method in detail. We have done these things in green melt as well, right? And then we have process capability indices. In this also we are going to look into either sigma level or CP-CPK or PP-PPK. So let us first understand what is a population and what is a sample. What do you mean by population? Population means entire data set of entire country or large data set across the globe also. Sample is a small subset of this population. And in population, if the data is large, for example, counting the number of Maruti Swift cars in India, it will be very tremendous data, right? It will be huge data. And it becomes impractical for us to look into the entire data to estimate the parameters. Right? That is when we actually look into sample. What is sample? Okay, I'll estimate the average number of cars per square kilometer. And then calculating the number of cars in a whole population by finding the product of area and the number of cars per square kilometer. In this way, I try to arrive at the entire population. I'll not go about counting how many Swift cars are there in India. And then we have data for all calls at a call center stored in a database. You cannot go ahead and review each and every call. For quality purpose, they listen to the calls, phone calls. Right? You cannot go ahead and listen to each and every call of a call center. That would not be possible. So that is actually population. A sample, you probably pick up some 10% of all the calls and then try to have a look at that. Then here are the formulae to calculate population parameters and sample statistics. In population parameters, you have mu, which represents the population mean. This is the formula. And whenever you calculate the sample mean, you use this formula. Remember, in population, you always use Greek letters. Unlike your sample, you use Greek letters for population. Then comes the population variance. In variance, this is the formula. But look at the change when we move to sample statistics, sample variance. If I want to calculate, this n gets replaced by n minus 1. That is the only difference. And we know that standard deviation is the square root of variance. Here also standard deviation is the square root of variance. All right. Mean versus median. When to use mean, when to use median. If the data has outliers, then mean is not a good indicator of central tendency. In these cases, use median. For example, let us calculate mean and median for this. Can you tell me what is the mean for the first data set, Anuj? 1, 2, 3, 4, 5, 6, 7. Can you tell me what is the mean for this?
3.5.
Sorry?
3.5.
Now, how did you arrive at 3.5? Mean. What is mean? 1 plus 2 plus 3 plus 4 plus
4,
5 plus 6 plus 7 divided by number of points. How many points do you have? 1, 2, 3, 4, 5, 6,
7.
7. Yeah. So if you sum up, I think it will be 28 by 7, which is nothing but 4. So the
4,
mean
yeah.
for this is 4. Calculate the mean for the second data set and tell me what is it that you're getting.
1 plus 2 plus. I'm doing in calculator.
Sorry?
I'm doing in calculator.
Yeah, yeah.
103.
721 divided by 7, right?
Yeah,
So it is
103.
721 by 7, which is 103. Look at the difference in the mean. The difference between this data set and this data set is only 1 point, that is this. 700, here we have 7. Rest all are same. So 6 out of 7 data points are same in the two data sets. However, look at the mean. Here it is 4 and here it is 103. Yeah, very huge difference. This is called as an outlier. This 700 is called as an outlier. When you have such extreme values, then mean is not a good indication. Yeah, that is when you go with your median. So what is the median in this data set? What is median? Median is
What is that?
nothing but
Yeah.
if you have odd number of values, that means here 7, there are
Mm.
odd number of
Mm.
values. Then you take the middle value as your median. So n
Okay.
plus 1 by 2 is the formula. Simple. N plus 1 by 2. How many do you have data points? 7. So 7 plus 1 by 2 is
7.
8 by
Mm.
2, that is 4. So what is the fourth number? 1, 2, 3, 4. Here also you have 7 numbers. So formula is 7 plus 1 by 2, which is equal to 8 by 2, which is 4. What is the fourth number? 1,
Mm.
2, 3, 4. Yeah, this is how you calculate. And for dispersion also, if the data has outliers, then you use range and standard deviation. Normally you use range and standard deviation, but if the data has outliers, then range and standard deviation are not good indicators to check what is the variation in the process. Instead, you will have to use IQR, interquartile range. And we have discussed about interquartile range when we discussed box plot, right? Yeah, sorry. So what is the range for this data set? 1. How do you calculate the range, Anuj? It's simple. Range is maximum value minus minimum value. What is the maximum value? 7. What is the minimum value? 1. So 7 minus 1 is 6. Here, what is the maximum value? 700. What is the minimum value? 1. 700 minus 1 is 699. So look at the huge difference. Just because of one data point, which is an outlier, the difference between the range is tremendous. Here you're getting 6, here you're getting 699. Right? Hence, range is not a good indication when you have outliers. Let us calculate the standard deviation as well. What is the formula for standard deviation, Anuj? Do you remember? Hello, Anuj, are you there?
No, I'm just trying to remember.
Yeah, no
I
problem.
write down somewhere.
Okay.
No, I'm here.
Yeah,
I'm here. I'm just trying to remember.
yeah, no problem. So I'll
What is
tell
that?
you.
You can just.
It is summation of xi minus x bar whole square divided by n minus 1. Okay, if you have a sample data set, if
Okay.
suppose this is the entire population, then our formula changes. It will be summation of xi minus mu whole square divided by n. Xi means it can take any value, right? So this is how you calculate normally. 1 is xi minus, what was the mean? Mean, we found out the mean, it came out to be 4 whole square plus second number is 2. So it's 2 minus 4 whole square plus it third value is 3. So it will be 3 minus 4 whole square plus fourth number is 4. So it will be 4 minus 4 whole square. Similarly 5 minus 4 whole square plus 6 minus 4 whole square plus 7 minus 4 whole square divided by total number of data points 7. That will give you your standard deviation. If you calculate standard deviation for these two numbers, it will give you two completely different numbers. Just because one number is different, you'll get two different numbers completely. Yeah, hence you use IQR, interquartile range. We can do this in Minitab. IQR. All right. Okay. Next thing is continuous data. For continuous data, we now need to work with area under the curve. So if I put the data, represent the data like this, let me select another value. So the total area under this curve, this total area, yeah, is equal to 1. This total area is equal to 1. Total area under the curve, right? And there are few other distributions that we need to be aware of. Continuous data can have several different distribution shapes. It can follow normal distribution, or it can follow exponential distribution, or it can follow something called as Weibull distribution. Yeah. Normal distribution is the most normal data distribution for a process. What if a process is not normal? If the data is not normal or the process is not normal, there could be some special causes governing it. Or the data may be unreliable. You may not do any analysis on that. Now you need to correct the situation before you do any statistical analysis on that. Another thing is, normal curve is a bell-shaped and symmetrical curve. When I say symmetrical curve, one thing is it's bell-shaped, no doubt about that. It resembles a bell. Now this curve represents or resembles a bell. That's fine. Symmetrical meaning, if this is the mean, this half and this half will look alike. Symmetrical. And I can simply represent any normal curve using mean and standard deviation. This is the standard notation. I can say the data is normal with mean mu and standard deviation sigma square. I can simply represent any normal distribution like this. Yeah. Next comes normal probability density function. We know that the entire area under the curve is 1. And we know that from -1 to +1, sigma, you have approximately 68% data. From +2 to -2 sigma, you have 95.45% of data. -3 to +3 sigma, you have 99.73% of the data. So 99.73% of the area under the curve lies within ±3 standard deviations from the center. And this is the function used to calculate normal probability density function. Just remember that formula. We'll not be using it exclusively.
I
But
was about to ask you that
yeah,
do I have to remember all these formulas or?
no, not required, Anish, not required. Formula,
Okay.
you need not remember it, but you'll have to remember the logic. This is
Okay.
the bell curve. Between +1 to -1 sigma, you have 68% of the data. Between plus and -2, this entire region data, if I want to find out, it will be 95%. ±3 sigma, it will be 99.73. These kind of things you'll have to remember. And this is the basic premise. Entire area under the curve is 1. Right? These kind of derivations formula you need not remember. Yeah. All right. What is standard
Just give
normal
me
curve?
1 minute.
Yeah, yeah.
Give me 1 minute.
Yeah, yeah.
Yeah, that.
All right.
Hello.
So yeah, Anuj. So for each and every normal curve, you'll have different mean and standard deviation. This is the mean, this is the standard deviation. For each and every normal curve, different curves have different means and standard deviations. But I do not want to use different means and standard deviations for each and every curve. So is there any way that I can standardize and represent all the normal curves using one mean and one standard deviation? Yes, there is a way to represent. In that case, we transform the normal curve to standard normal curve. Yeah, so in standard normal curve, all the normal curves will have mean is equal to 0 and standard deviation is equal to 1. That is Z transformation. You call that as Z transformation. All x values from a normal distribution curve can be transformed to the corresponding Z values using the formula this. X minus mean by standard deviation. X minus mean by standard deviation. Simple. All x values. For all the values you can use this, you can do this and represent all the normal curves using standard normal distribution. Okay, let us do this simple exercise. Calculate probability for the variable. This is the x which is less than 5. So if this is the line, I want to find out this region. X less than 5 for a normal distribution where mean is 15 and standard deviation is 5. And we need to calculate the area for all values of x which are less than 5. This can be obtained by cumulative probability. So we want to calculate probability of x less than 5 with a normal distribution whose mean is 15 and standard deviation is 5. Let us do that now. Using Minitab, let us just calculate this and see what is the value that we are going to get. So here are the details that are given. Approach 1 is calculate probability distribution normal. So let me open the Minitab. It's taking time to load. Yeah.
The parameter 2 distribution vary probability. Which one do you want? There are 4 options. Vary.
Normal distribution.
No, it says very single, very parameter, 2 distributor.
All right. So
Very
please,
view probability.
please follow me, Anuj. I'm showing you the details once again. Just follow me. So this is a Minitab, right? I've asked you to go to graph, click on probability distribution plot. Have you clicked on this? Or have you
Yes.
clicked on another option?
No, no, I click on.
Okay, I clicked on this. So you'll have to click on view probability because I want to view the probability, right? Click on OK. Yeah. Then you do that. Okay. So in the mean, you put it as 20. Mention. Yeah, and type 3.5 in standard deviation.
Okay.
Have you done that? Now click on shaded area.
Yes.
What do you want to calculate? You want to calculate the probability for the pizza delivery within 30 minutes.
Yes. Yes.
So less than 30 minutes probability you want to find out. So what will you select in that? Right tail or left tail? I want to calculate less than 30 minutes.
The left tail.
Left tail.
Yeah.
Select left tail.
Left tail.
What is the x value? You'll have to select x value on the top. click on that X
Okay.
value, select the radio button X value, and then below you will have a field wherein you can enter that X value number. In that field, enter 30 minutes.
But then when I select the X value, instead of instead of left tail, it has highlighted the right tail. Is it okay?
Again, select the left tail.
Okay. Okay. I select.
Okay, X value is 30. Select the left tail and click on OK. Tell me what is the probability?
0.9979.
Absolutely correct. 99.79% of the times pizza will be delivered within 30 minutes. All right. Yeah, that is the case. Look at the second example. See my screen. The company has announced a self-imposed penalty of rupees 200 for every delay beyond 30 minutes. Determine the overall loss if there are how many? 1 lakh deliveries in an year. Right? If it is beyond 30 minutes, for every pizza that is delayed, company will pay a penalty of 200. And there are 100,000 deliveries in an year. These kind of problems do come. Okay. So it's the same problem extension of that. So go back to your mini tab.
Shall I go back?
Go back to your mini tab. Go to graph, probability distribution plot.
Do you want me to do it?
Yeah, please.
Okay.
Go to graph,
Go to the
probability
probability
distribution plot, view probability, and click on OK. Mean and standard deviation will, sorry?
Yeah, it says mean 20, standard deviation 3.5.
Yeah,
right?
that's the same, right? See my screen once, please. Mean is 20, standard deviation is 3.5. We are doing for the same problem. Okay. They want to find out how many have exceeded 30 minutes. Okay. So I go to the shaded region. Greater than 30 minutes, I'll select right tail. Click on OK. What is the value that you have got? Probability value.
0.002.
Correct.
Shall I do it? Huh?
Yeah. 0.002137, right? This is the probability for what? 100 pizzas. If I deliver 100 pizzas, approximately 0.21 pizzas will not be delivered on time. So 0.21 multiplied by 200 rupees is the penalty, right? For each delay. You multiply it by 200. So for every 100 pizzas, you will get to know what is the penalty that you are paying. So for 1 lakh, how many? Simple, multiply it by 1000, you'll get to know. Clear, Anush?
Yeah.
So these kind of problems also do come, and you as a Six Sigma consultant should be well versed with the probability kind of things also, so that it's easy. All right. How to calculate DPMO and the normal curve? This is one interesting part, and then we can stop. Okay. Step 1. DPMO is given. Calculate the number of defects for one opportunity. This is the defects area to the right of the line. This is the line. Right? If I give you defects per million opportunities, if I ask you to find out the number of defects for one opportunity, it's the defects to the this region, right region. Step 2, you can calculate the cumulative area to the left of the line by subtracting from 1. This entire area is equal to 1, right? So 1 minus this region will obviously give me this entire region. So if I want left region, I'll do just 1 minus that region. Then step 3, use a normal curve to estimate the z value that corresponds to the cumulative area identified in step 2. And how do you calculate? Using simple thing. I mean, case study has not come to us yet. Once the case study comes, we'll do that. So using inverse cumulative probability in Minitab, you use this. Go to calculate probability distributions, normal. Or you can just use graph probability distribution plot. Remember, these are the steps, that's it. So here is our exact problem. Only DPMO is given to me. I will have to calculate the z value. How do I do it? Yeah, how do I do it? Let me go back to that. All right, this is my DPMO. I will have to calculate the z value. Area to the right is so much. How did I find out that area to the right? I need to calculate number of defects for one opportunity. How do you calculate for one opportunity, Anuj? This is for million opportunities, DPMO. Defects per million opportunities for 1 million.
Just give me 1 minute, yeah.
Yeah, yeah.
Barney, 1 minute, yeah?
Yeah, no problem.
Yeah, back, Barney, sorry.
No problem at all. No problem. Yeah, Anuj. So I was telling that 232695 are the number of defects for million opportunities. If I want to find out defects for one opportunity, what would that be? It will be 0.232695. Defects per million opportunities is so much. Defects per opportunity will be so much. Simple, divided by 1 million. If you want to know for one opportunity. All right, Anuj? Or is it, if it's not clear, let me know.
We have to divide by 1 million, is it? That's it.
Correct, that's it. Then I'm getting this value, 0.232695.
Okay. Sorry, one repeat. Okay,
Yeah.
DPMO and calculate the z value. So we have to divide by 1 million, is it?
No. So this is defects per million opportunities. Okay. So if defects per million opportunities are given, step 1, we are into step 1. We have to calculate z value. That is a final goal. In order to go to the final goal, let me calculate the first step, that is calculate the number of defects for one opportunity. So let me go here. So DPMO is so much, defects per million opportunities. If I want to calculate defects per opportunity, it will be 232695 divided by 1 million. 0, 0, 0. If I divide it by 1 million, I get this value. Is this clear?
1 million is 10. 1 million is 10 lakhs, right?
Yes, absolutely. Yeah, is the first step clear?
Yes.
Let us go to the second step. Calculate the cumulative area to the left of the line by subtracting from 1. This entire region will be 1. Area to the right is given to me. Area to the right is how much? 0.232695. which is nothing but this value given here. Okay, this value is given. So if I want to find out the area to the right of this region, so what do? This entire region is 1, I know that. This entire region is 1. I want to find out to the left of this. So I'll simply do 1 minus this value.
Yeah.
1 minus this, if I do, what is the value that I'm getting? I'm getting this value. 0.767305. Right? Now all I will have to do is go to mini tab. Go to calculate probability distributions, normal. Alright, what was the mean standard deviation given? 0 and 1, because this is standard normal distribution. Sorry. This value is 0.767305. Remember, 767305. So I'll give that value. 0.767305. Is that correct? 767305. That's correct. Yeah, I'll just do an OK. I'll get a value. 0.778. 767305. Why am I getting the X value as 0.73? Did we do something wrong somewhere? One second, Amish. Probability normal, that is what I've done, right? Probability R1. 0 and 1, I have given an input value 767305. Alright. Fine, the same value I'm getting. So this is the Z value. 0.778550. Okay. Yeah, perfect. So ZLT will be how much? Let me just quickly replace this. Oh. .77 is the ZLT value for me. This is how you calculate sigma long term ZLT. Don't worry. Just keep revising whatever topics we are discussing, Anuj. By the end, you'll become perfect on that. And so if I give you DPMO and if I ask you to calculate the Z value, this is how you'll have to calculate. Okay. Now, there is a problem given to you. DPMO is 120,000. You'll have to calculate the Z value.
Can we do it now?
No, you'll have to do it as an exercise. And then you can also refer to this. I will tell you how to refer to this and come up with those values. So don't worry. So just do it until here, Anuj. Given DPMO is 120,000